Hello everyone, my name is Naina and I'm from the Padu Academy. So, in today's video, we'll see the D and F block elements, continuation of that, and in today's video, we'll see about the oxidation states. Now, oxidation states means the ability of a molecule to share or lose its electrons is what we show them in the form of oxidation states. So, it is a notable feature of the transition elements. So, here the trend you can see is that it gradually there is an increase in oxidation states and then we can see there is a decrease, right? So first it increases and then it decreases. Okay, this is what the oxidation state trend is. Now the elements which give the greatest number of oxidation states occur near the middle of the series, that is manganese. Basically the ones which show greater number of oxidation states are basically seen on the middle of the series. For example, manganese, it shows the oxidation state of 2 to 7. That is the maximum of the oxidation state. Now, it decreases when you go towards the end, right? Here you can see it decreases as we go towards the end of the molecules. That is basically because there are very few electrons. Okay, there are few electrons to lose or share. That's why it decreases as we go. I think it shows only basically oxidation in transition elements. It is calculated by the addition of both. It is a sum of S and D electrons. Okay, up to manganese this is followed, but after manganese, as you can see, the orbits they start getting filled continuously, so the availability of electrons to be removed or the nuclear charge which increases, and hence the enthalpy also increases, ionization enthalpy also increases, so there is a difficulty in removing or sharing the electrons, and this number of electrons goes on filling up the orbitals. So zinc basically has shows a plus 2 where no d electrons are involved, only s orbitals are involved. Okay. Now, the variability of oxidation states of characteristic of transition elements arises out of incomplete filling of d orbital. Now, the characteristic transition that there is a decrease and then increase. There is an increase and then a decrease. That characteristic of transition elements, it arises out of the incomplete filling of d orbitals. Okay, in such a way that the oxidation states differ from each other by unity. But in other non-transition elements it shows a difference of unit of 2. Okay, 2 units ka difference it show, but in transition it shows 1 unit ka difference. Okay, now the trends in the standard electrode potential, okay, is basically the thermochemical parameters which is related to the transformation of solid metals, that is M2 plus ions into the solution, and their standard electrode potential. Now here we calculate the E naught values, that is the electrode potential values. For example, copper. Okay, copper does not have the ability to remove the H2 atoms or hydrogen atoms from the acid because of its positive electrode potential. Hence, it can only react with the oxidizing acids like nitric acid and concentrated sulfuric acid, which are later reduced by copper. Now, the high energy to transform copper to copper 2 plus is not balanced by its hydration enthalpy. Hydration enthalpy is the removal of hydrogen. Okay, the energy to transform copper to copper 2 plus ion, which cannot be balanced by hydration enthalpy, is because hydrogen from the acids. Okay, now the general trend towards the less negative E naught. Now, because of positive, it does not take any part in the balance, right? But the negative E naught. Okay, negative E naught values across the series is related to the general increase in the sum of first and second ionization enthalpy. Okay, when you get a negative series or negative electrode potential in the series, it is basically related to the increase. Okay, increase in the sum of first and second ionization enthalpy. The energy to remove two electrons, first and second electrons, the overall energy will increase, and that will give you a negative electrode value. Now, it is interesting to note that the value of E naught for Mn, that is manganese, nickel and zinc, are more negative than expected from the trend. So these molecules, that is Mn, that is manganese, nickel and zinc, they show a more negative E naught value because their first and second ionization enthalpy increases. Now, stability of the half-filled d subshell of manganese and completely filled d orbital of Z and zinc are related to their E naught values, whereas E naught of nickel is related to the highest negative hydration energy. Now, why they show the highest negative electrode potential for manganese and zinc? It is because of their half-filled and completely filled d orbital configuration, and for nickel it is basically because of the highest negative hydration energy or hydration enthalpy. So nickel can remove hydrogens easily. Okay. Now, next is the trends in M3 plus and M2 plus standard electrode potential. Now, first we have seen from the M2 plus and M, that is metal to metal 2 ions. Now here metal 2 plus and metal 3 plus. Now the low value of scandium reflects the stability of SEC3 plus, which has a noble configuration, noble gas configuration. Now the low value of scandium reflects on its stability, that is scandium 3 plus, which has a noble gas configuration. Scandium 3 plus has a noble gas configuration. And the highest value of zinc is due to the removal of an electron from the stable d orbital configuration of Zn2 plus. Now Zn, the highest value for zinc, okay, is due to the removal of an electron from the stable D10 configuration of the zinc 2 plus. Now zinc 2 plus, here there is a removal of electron from the stable D10 configuration. That's why it shows the highest value. And the comparatively high value of Mn, that is manganese, shows that Mn2 plus D5 is partially stable, whereas comparatively low value of Fe shows the extra stability of Fe3 plus. Now Mn2 plus will have comparatively high value because it already has a half-filled d orbitals. Now iron will also show an extra stability because when it goes to Fe3 plus form, it also has a half-filled d orbitals. Hence, Fe3 plus is more stable than Fe2 plus. Okay. The comparatively low value of vanadium is related to the stability of V2 plus, where half-filled T2G level is there. Now, regarding this T2G level, you will be seen in unit 5. Okay. Now, the low value of vanadium is basically because of the stability it gets through V2 plus configuration or oxidation states. Now, trends in stability of higher oxidation states. Now, this table, it shows the stable halides of the 3D series. Now, how these are the stable halides. I hope you have learned about haloalkanes, haloarenes, right? So these are the stable halides. Halides are fluorine, chlorine, bromine, iodine are all the halides. Now, the highest oxidation number is achieved in titanium X4, that is tetrahalides. Okay, titanium tetrahalides, vanadium pentafluoride, and chromium hexafluoride. Now, the 7 plus state of manganese is not represented in simple halides but in MnO3F is known as is known, and beyond Mn, no metal has the trihalide except iron and cobalt. Now these are the basically the oxidation states, higher oxidation state which forms the halide compounds with them. Okay. The ability of fluorine to stabilize the highest oxidation state is due to their higher lattice energy in case of COF3 or higher bond enthalpies in terms for the higher covalent compounds, for example, V5, VF5 and CrF6. Basically, these halides, they are used to stabilize the molecules. Okay. So in our next class, we will see about the chemical reactivity and magnetic properties. So in this class, we have seen about oxidation states and their how to stabilize them and their trends in standard electrode potentials. So thank you for watching my video. Please do like, share and subscribe to our channel.